Hey folks, Kellen Riley here. I'm going to try and study some cryptography and give you some insight into how I study. The book is Cryptography Made Simple, so I'd like to learn more about cryptography. And here's chapter 1. It says, much of this book will be spent looking at the applications of modular arithmetic, since it is fundamental to modern cryptography and public key crypto systems in particular. So already I have a question. What is a public key crypto system? Alright, hence in this chapter we will introduce the basic concepts and techniques we shall require. So this chapter is supposed to be basic. I'm not sure I'm going to understand anything because I've read this chapter before and the knowledge I gained was pretty close to zero. So we'll keep going here. The idea of modular arithmetic is essentially very simple and is identical to the clock arithmetic you learned in school. For example, converting between the 24-hour and 12-hour clock systems is easy. One takes the value in the 24 clock system and reduces the hour by 12. For example, 1300 in the 24-hour clock system is 1 o'clock in the 12-hour clock system, since 13 modulo 12 is equal to 1. So we have this idea of a modulus operation, and I think I know a bit about that. So let's just say 5 mod 2. So how many times does 2 go into 5? Well, it goes into 5 2 times with 1 left over. Since 2 times 2 is 4 plus 1 is 5, the 5 mod 2 is equal to 1. So that's what I understand there. Okay. More formally, we fix a positive integer n, which we call the modulus. So in my little example there, 2 was the modulus. For integers a and b, we write a equals b mod n if n divides b minus a. And we say that a and b are congruent modulo n. Often we are lazy and just write a equals b if it is clear we're working modulo n. So I'm not going to lie, that those two sentences right there threw me for a loop. So let's say it says, more formally we fix a positive n, integer n, which we call the modulus. For two integers a and b, we write a equals b mod n if n divides b minus a. And we say that a and b are congruent modulo n. Often we are lazy and just write a equals b if it is clear we're working modulo n. So there's a little equation here, a equals b mod n. If n divides b minus a. So let's just take a concrete example, right? I'm getting a little confused. So let's say 5 mod 2 is equal to 1. 11 mod 2 is also equal to, so 2 goes into 11, 2, 4, 6, 8, 10, 5 times with 1 left over. So they'll say that 5 equal to congruent to modulo 2? 5 congruent modulo 2? See, I get confused because these two sentences don't make much sense to me. So, what do you do in a textbook when you come across something you don't understand? Well, you try to investigate it further and try and find out where your misunderstanding is. My misunderstanding is just in the way they're using the language. We say that A and B are congruent modulo n. It's just not computing in my little box here, my head box, so best to just move on. We can also consider mod n as a postfix operator on an integer which returns the smallest non-negative value equal to the argument modulo n. For example, 18 mod 7 is 4, so let's see, 18. And they have parentheses here, I'm not sure why, mod 7. So 7 goes into 18 twice, and 18 minus 14 is 4. So 18 mod 7 is 4. Now they have negative 18 mod 7. Again, 7 goes into 18 two times, and negative 18 minus 14, whoops, negative 18 mod 7 equal to 3. Really not sure how they got that. Why is negative 18 mod 7 equal to 3? I couldn't tell you. It just is. Alright. The modulo operator is like the C operator %, except that in this book we usually take representatives which are non-negative. For example, in C or Java we have negative 3 mod 2 equal to negative 1. Whilst we shall assume that negative 3 mod 2 equals 1. For convenience, we define the set. Okay, so there's a set Z divided by n over Z equal to 0, comma, dot, 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 n minus 1. This is something I do understand. For example, if you take 18 mod 7, the possible answers for that would be 0, 1, 2, 3, 4, 5, and 6. So I do understand that much. Okay. As the set of remainders modulo n. This is the set of values produced by the postfix operator mod n. Note some authors use an alternative notation of z subscript n. Let's see, so z subscript n. Z subscript n for the set z over nz. However, this book we shall stick to z over nz. So that's just the set of remainders produced by a modulus operator. So that much I do understand. For any set S, we let number S denote the number of elements in the set S. Thus, the number of elements in z slash nz is equal to n. So right, if you had 18 mod 7, there's going to be 7 elements in z over z nz. There's going to be 0, 1, 2, 3, 4, 5, and 6. And so the number of elements here is 7 elements. Okay, I think I understand that. So let's get rid of this. Okay, that's the first page down. We got a lot to go here. The set z over nz has two basic operations on it, namely addition and multiplication. These are defined in the obvious way. For example, 11 plus 13 mod 16 is equal to 24 mod 16, and 16 goes into 24 once with 8 left over, so that equals 8. Since 24 equals 1 times 16 plus 8, and 11, so this is times 11 times 13 mod 16 equals, so 11 times 13, they just give it to us, it's 143 mod 16 equals 15. So apparently 16, if we break out our little calculator here, 143 divided by 16. So 16 goes into 143 8 times. 16 times 8 equals 128, and 143 minus 128 is 15. Okay. That makes sense. We can add or subtract, we can add or multiply when we're dealing with modulus. Okay, groups. Now this is the section that really throws me for a loop, because there's lots to remember with groups. Addition and multiplication modulo n worked almost the same as arithmetic over the reals or integers. In particular, we have the following properties. And here we get a bunch of symbols, so I'm going to get confused. Addition is closed, so it says, I do know how to read some of this, for all a, b belonging to the set z divided by n over z, we have a plus b is in the set z over nz. So let's just take an example, right? We have 18, let's do our 18 mod 7. Then we have our 7 elements, 0, 1, 2, 3, 4, 5, and 6. If we take any element, like 0 and 1, take any two elements and we add them together. 0 plus 1 is just 1, and 1 is in this set. So z z over 7 and z is this, right? This set. We have for all a and b, but I'm a little confused here, because what if we took a equal to 6, a equals 6, and b equal to 5, right? Well, 6 plus 5 is 11, and 11 is not in this set, right? So I really don't understand this first property of groups. Addition is associative. For all a, b, and c in z over nz, a plus b plus c is equal to a plus b plus c. And we can take a plus b first, or we could take b plus c first, and it wouldn't matter. 0 is an additive identity, so a plus 0 is equal to 0 plus a is just equal to a, so that makes sense. The additive inverse always exists. For all a in z over nz, a plus n minus a equals n minus a plus a equals 0. So you can cancel out the elements, right? i.e. negative a is an element which when combined with a produces the additive identity. Okay. So if I had some set like negative 1, 2, negative 2, or let's do negative 3, negative 2, negative 1, 0, 1, 2, 3. If we took a equal to negative 3, then there exists some b like 3, so negative 3 plus 3 is equal to 0. This is where it gets sticky for me, folks. I'm trying to learn here, but I'm not doing very well. Multiplication is closed. For all a, b, z, for all a, b in the set z over nz, a times b is also in the set z over nz. Okay, multiplication is associative. A times b times c is equal to a times b times c. You can take a times b first or b times c first, it doesn't matter. 1 is a multiplicative identity. For all a and z over nz, a times 1 equals 1 times a equals a. Multiplication and addition satisfy the distributive law. For all a, b, c, and z over nz, a plus b times c is equal to a times c plus b times c. So right, that's just the simple distributive property that we learned in math, right? We can say a times b plus c is equal to ab plus ac. Okay, I think I understand that. We'll see as I move along whether or not my understanding is correct. Alright. Multiplication is commutative. A times b equals b times a. Okay. Many of the sets we will encounter have a number of these properties, so we give special names to these sets as a shorthand. Okay, definition 1. This is important. Groups. A group is a set with an operation on its elements, which is closed, has an identity, is associative, and every element has an inverse. A group which is commutative is often called abelian. Almost all groups that one meets in cryptography are abelian, since the commutative property is often what makes them cryptographically interesting. Hence, any set with properties 1, 2, 3, and 4 above is called a group, whilst a set with properties 1, 2, 3, and 5 is called an abelian group. Standard examples of groups which one meets all the time in high school are the integers, or the reals, or the complex numbers under addition. Here the identity is 0 and the inverse of x is negative x, since x plus negative x equals 0. The non-zero rational, real, or complex numbers under multiplication. Here the identity is 1 and the inverse of x is denoted by x raised to the negative 1, since x times x raised to the negative 1 equals 1. A group is called multiplicative. A group is called multiplicative if we tend to write its group operation the same way as one does for multiplication, i.e. f equals g times h, and g raised to the fifth equals g times g times g times g times g. We use the notation, so here's some notation, g comma times. In this case, if there is some ambiguity as to which operation on g we are considering. A group is called additive if we tend to write its group operation the same way as one for addition, i.e. F equals G times H, and 5 times G equals G plus G plus G plus G plus G. In this case, we use the notation G plus if there's some ambiguity. So what's ambiguous here? Okay, I'm not sure. An abelian group is called cyclic if there's a special element called the generator, from which every other element can be obtained either by repeated application of the group operation or by the use of the inverse operation. For example, in the integers, okay, so integers, so that would be like dot dot dot, -3, -2, -1, 0, 1, 2, and 3. Every positive integer, so 1, 2, and 3 in this case, let's see, comma, dot, dot, dot. These are the integers, right? Every positive integer can be obtained by repeated addition of 1 to itself, e.g. 7, it can be expressed by 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. Right, so -3 could be obtained by -1 plus -1 plus -1, right? So, is 1 the generator? Yeah. So under the set of real numbers, 1 is the generator for this set, because every other element can be obtained by either repeated application of the group operation or by the use of inverse operation. Okay. Every negative integer can be obtained from a positive integer by application of the additive inverse operator, which sends x to -x. Hence, we have that 1 is the generator of the integers under addition. Oh, okay, so I did conclude the right thing there. If G is the generator of a cyclic group G, alright, I got confused. If G is a generator of the cyclic group G, we often write G equals, and then there's this weird angle bracket stuff. G equals G. If G is multiplicative, then every element H of G can be written as H equals G raised to some power. List of G if additive, then every element of H of G can be written as X times G, where X in both cases is some integer called the discrete logarithm of H to base G. I'm not going to pretend I understand any of that, but we'll move on. Rings. As well as groups, we also use the concept of a ring. Rings. A ring is a set with two operations, usually denoted by plus and times for addition and multiplication, which satisfies properties 1 to 9 above. Oh man, okay, we have 9 properties to keep track of now. I'm getting real confused. We can denote a ring and its two operations by the triple R times plus. So here's some notation. R times plus, this is a triple apparently. It also happens that multiplication is if it also happens that multiplication is commutative, we say that the ring is commutative. This may seem complicated, but it sums up the types of sets one deals with all the time. For example, the infinite commutative rings of integers, real or complex numbers. In fact, in cryptography, things are even easier since we only need to consider finite rings, like the commutative ring of integers modulo n, z over nz. Thus, z over nz is an abelian group when we think only of addition, but it also is a ring if we want to worry about multiplication as well. Okay, folks, I'm going to take a smoke break because I'm too stressed out by all this crap. And to be clear, it's not crap, it's just that's my own frustration about this subject coming forward. So we're going to smoke a cig. I'm going to smoke a cig and contemplate rings and groups, addition and multiplication over the real numbers, modulus. I'm going to contemplate that. Not sure I'm learning much here, but it's not the book's fault, it's my own fault, right? I am a hard person to teach. And I'm trying to teach myself out of a book, which I've been able to do in the past, but I'm struggling right now. Euler's function, and I do know how to pronounce Euler right. In modular arithmetic, it will be important to know when given a and b, the equation a times x equals b mod n has a solution. Okay, we're given a and b, so let's say a is equal to 5 and b is equal to 3. So 5 times some x equals 3 mod, I don't know, 7. How many 7s go into 3? 0, with 3 left over, right? So we got 3, so we got 5 times x equals 3, and x equals 3/5. Has a solution. For example, there's one solution in the set z over 143 to the equation 7 times x equals 3 mod 143. But there are no solutions to the equation 11 times x equals 3 modulus 143. However, there are 11 solutions to the equation 11 times x equals 22 modulus 143. What? What did I just read? Okay, we'll keep going. Luckily, it is very easy to test when such an equation has one, many, or no solutions. So, there's either one, many, or no solutions. We simply compute the greatest common divisor, GCD, of a and n, i.e. GCD a and n. So, for example, we have an example here, so let's use it. Alright, we got, maybe I'll use text here, because my writing is sloppy. 11 times x equals 22 mod 143. And they've got parentheses here. Might need another cigarette. If GCD of a comma n equals 1, then there's exactly one solution. So GCD greatest common divisor of 11 and 143. Let's see, 143 divided by 11 is 13. So 11 is the greatest common divisor of 1143. Therefore, there are 11 solutions to the equation 11 times x equals 22 mod 143. Okay. If GCD of a and n equals 1, there's exactly one solution. We find the value c such that a times c equals 1 mod n, and then we compute b times c mod n and store it in x. If g equals GCD a of n not equal to 1 and GCD of a of n divides b, then there are g solutions. Here we divide the whole equation by g to produce the equation a prime times x prime equals b prime mod n prime, where a prime equals a over g, b prime equals b over g, and n prime equals n over g. If x prime is the solution to the above equation, then x prime plus I times n prime is stored in x, for g0 less than I less than g is a solution to the original one. Otherwise, there are no solutions. Well, I sort of just plowed right through that, which is probably one of the reasons why I'm not understanding any of this. In the case where GCD a of n is 1 is so important we have a special name for it. We say a and n are relatively prime or coprime. So 11 and 43 are coprime. No, they're not coprime. Nope, they're not coprime. I misspoke. In the above description we wrote x arrow y, so x arrow y, to mean that we assign x the value of y. So this is like some pseudocode that they're introducing here. This is just to distinguish it from saying x equals y, by which we mean x and y are equal. Clearly, after assignment of y to x, the value of x and y are indeed equal. But imagine we wanted to increment x by 1, we would write x plus 1 into x, the meaning of which is clear. We assign the value x to x plus 1, okay, whereas x equals x1 plus 1 is possibly a statement which evaluates to false. So right here they're just from what I understand, they're distinguishing between what an arrow means and what an equals means. So y stored in x is not the same as y equals x, right? So my programming background is coming in helpful here. Another reason for the special notation of assignment is we can extend it to algorithms or procedures, right? So for example, a input z stored in x might mean we assign x the output of procedure a on the input of z, right? This procedure might be randomized, and in such a case we are thereby assuming an implicit probability distribution of the output x. We might even write s stored in x, where s is some set, by which we mean to assign x a value from the set S chosen uniformly at random. Thus, our original y stored in x notation is just a shorthand for the set y stored in x. The number of integers in Z over NZ which are relatively prime to n is given by the Euler function. I cannot upset the math nerds by mispronouncing Euler's name, right? Given the prime factorization of n, it is easy to compute the value of Euler n. If n has the prime factorization, n equals, I don't know what this symbol means. Let's see. So we have n equals this thing, and I equals 1 p sub I raised to the e sub I. Then Euler of n, Euler of n equals n over this thing, I equals 1 p sub I raised to the e sub I times p sub I minus 1. Note that the last statement is very important for cryptography. Alright, I'm going to do some research here. I do not know what this symbol means. What does the... How do I even ask this question, right? What does the double I symbol mean in math? No fucking clue. Does it mean, I'm gonna guess, this means something times something times something times something? Well, that's what I'm gonna guess, because there is no definition of this symbol as of yet. Note the last statement is very important for cryptography. Given the factorization of n, it is easy to compute the value of Euler n. The most important cases for the value of Euler of n in cryptography are: 1. If p is prime, then the Euler of p is p minus 1. So I think I can understand that, 3. Euler of 3 equals 2. Right? And if p and q are both prime, then p is not equal to q, then Euler of p times q is equal to p minus 1 q minus 1. So let's take, so Euler of 3 times 2 is equal to 2 times 1. Alright folks, there's a lot of stuff to go on here. They have problems, Chinese remainder theorem, Lagrange symbol. Let's see, algorithms, probability, birthday paradox, further reading. I'm wondering if there's like an exercises section at the end of these chapters. I'm not seeing any exercises. Chinese remainder theorem. Alright folks, that's all the study I can handle for now, so I'm going to quit here. We just talked about what the Euler function, Euler's function, maybe watching a YouTube series about this cryptography stuff would be more my style of learning. But are there styles of learning, or is there just simply reading and learning? I don't know. I'm going to quit now and maybe pick this up later. Thanks. Bye.